Hello, IME 146 students. Welcome to week number 6's pre-lab. This week, we're going to talk all about abrasive manufacturing processes. So far, we've been through conventional manufacturing processes, so sawing, drilling, milling, turning, and broaching, back from IME 145. We've also used them this quarter to make some of our parts in our Geneva wheel. But then we went ahead and covered the non-traditional machining processes, the ones that don't use shear stress to remove material from the workpiece. So they use mechanical, electrical, chemical, and thermal energy to remove that material. Now today, we're going to the third subset of machining processes. Actually, it usually goes conventional, abrasive, and then non-traditional in terms of selecting a process. So you always want to start off with the conventional manufacturing processes or machining processes. If you can't get it done with the conventional, you look into the abrasive processes. If you can't get it done with the abrasive, you might be able to get it done with the non-traditional, or a combination of all three could be the case. A lot of parts have conventional, abrasive, and non-traditional performed on the one single part in order to produce the final features on the part that the engineer intended. So abrasive processes are we're gonna focus on this week in week 6's pre-lab here. And if you've been to the beach, you know what an abrasive is. It's like a piece of sand. In fact, silicon oxide sand is going to be one of the most simple natural abrasives we can use in machining. Now, before we talk about the specifics of these abrasives, let's just talk about abrasive machining in general. If the machining process, such as sawing, drilling, milling, or turning, can't produce the required dimensional accuracy or as nice of a surface finish that's required, we might have to go to the abrasive processes. Or if the workpiece has been heat treated, it's been hardened, or maybe it's too brittle to process with the basic conventional processes, we might bring in an abrasive to remove a small amount of material with that abrasive grain. Now, all an abrasive is a small hard particle that has an irregularly shaped edge, and that irregularly shaped edge is going to shear a little bit of material off your workpiece. So they're hard crystals, basically. That's all an abrasive is. And they're either manufactured synthetically, a synthetic abrasive, or they're manufactured naturally, natural abrasives. Like in our water jet last week, in week 5, when we did the water jet lab, we used garnet, which was a natural abrasive. In fact, it was an 80 grit size garnet, and that was the size of it. And again, because of its garnet, it's a natural grain, we can throw it down the drain when we're all done, or throw it in the garbage can. We don't have to go ahead and get it specially removed or treated afterwards like we would with the cutting fluids at our CNC mills and so forth. So these abrasive grains remove small amounts of material from the surface, and it produces a really tiny, small chip. Now, these abrasives, they're also used to hone, lap, buff, or polish workpieces. So if you remember when we talked about surface processes or surface finishing treatments in IME 145, we talked about lapping and polishing. That is an abrasive process as well. So we're going to talk about lapping at the end of today, at the end of this lecture, because that's the most precise abrasive process that we can perform on our workpieces. We can lap them to a really tight tolerance. So we'll talk about that here coming up in a few minutes. But before we get to the finest manufacturing process, lapping, let's talk more about abrasives. These abrasives, the natural ones out there, like emery, alumina, garnet, zirconia, quartz, those are going to be natural abrasives. Even walnut shells are used for natural abrasives. So in my tumbler in the lab, I have walnut shells impregnated with rouge, which is a polish. So the walnut shells and the rouge basically act as an abrasive on the surface of the workpiece to polish it really shiny. Now, there's some synthetic abrasives out there. They're used for the harder to cut materials. So there's like aluminum oxide, silicon carbide, cubic boron nitride, there's diamond, and even zirconia as well there. There's synthetic and natural zirconia. So we've got basically synthetic and natural abrasives. Now they have to get applied to the actual workpiece in 3 different forms. So these abrasive products can either be bonded in like the form of a wheel, a cup, or some sort of stick. So you bond the abrasive into some sort of form. Like in my toolbox right here, just thought about this. I have an abrasive sharpening stone. So this is literally just a stick of abrasive. It's a stone that I can use to sharpen or hone knives if I needed to. So, or cutting tools, or I can stone down a little raised surface on my CNC machine table. So that's an example of a bonded abrasive right there. It comes in a stick, ring, cup, stone, something like that. Now, abrasives can also be coated on some sort of backing made of paper or cloth. If you've ever used sandpaper, that's what I'm talking about. Coated abrasives would be an example of abrasive paper. It's not really sandpaper because we're not putting sand on the paper. We're putting an abrasive grit. So the abrasive paper can come in a sheet, a strip, or a belt. And we'll end up using coated abrasives and bonded abrasives when we start making air motor parts in the lab during week 6. In fact, we'll have a bonded wheel when we cylindrical grind or centerless grind the pistons. And then we'll have a belt with abrasives coated on it to go ahead and chamfer the tool steel main shafts when we get to that point. So we're going to use bonded and coated abrasives quite a bit over the next couple of weeks in the lab. Now, sometimes you can go ahead and have the abrasive be loose. If you remember the bead blasting from IME 145, where we abrasive media blast the part, that's what I mean by a loose abrasive. So it's held in some sort of liquid or solid carrier, and it's propelled by centrifugal force by either air or water pressure. So you're basically shooting the workpiece with abrasives that have either air or water behind it. So in the case of the water jet, it used water pressure with an abrasive grain in it. In the case of the sandblasting unit, it's using a loose abrasive with air to blast the abrasive against the surface of the part, make a nice satin finish. So those are the 3 forms that the abrasives come in the industry for manufacturing there. Now, the size of the abrasive is going to make a difference on the actual surface finish of the part. The bigger the actual grain size is, the worse your surface finish is. So you actually specify the grain size is specified by a number called the grit number. So the smaller the grain size, the larger the number. Has to do with how many you can fit in 1 square inch of material right there. So that like 80 grit would be the 80 grit abrasive size that we used in the water jet last week. Well, if you look at the back of abrasive paper, it's got a number. So the smaller the grain size, the larger the number. So if you're going to go in like wet sand, maybe gel coat for a boat, or you're going to wet sand clear coat on a car, you want to go ahead and have a grit number of 2,000 or 3,000, a really high number. In fact, like 3,000 is one of the highest numbers I've seen for grit size. Then I'm sure they probably have a little bit higher than that, but then if you want to rough or remove a lot of material, you go down to like a 60 grit, a really coarse grit. So the bigger the grain, the more it's going to remove. The smaller the grain, the less it's going to remove, the better the surface finish. Now, the most popular form of abrasive machining is grinding. In the grinding process, you have abrasive grains mounted to an actual wheel of some sort. And that wheel has to go ahead, it's been bonded. And that wheel has porosity in it. So what you have there is you have a specific abrasive that's been designed to machine a specific type of workpiece. So if you were to ever go into the hangar and you see some of the grinding wheels, it says, do not grind aluminum on this wheel. That's because the grinding wheel has been made for ferrous materials or ones with iron in them. So if you were to grind aluminum on a wheel that's been designed to grind steel, chances are you're going to melt the aluminum, and the aluminum is going to get into the porosity of that wheel because all they are just bonded together and there's a little bit of porosity. Now, if you get the aluminum melted into the porosity of the wheel, you're going to get an unbalanced condition. And the wheel is going to explode in your face and could damage the equipment or hurt you. So you want to make sure when you're grinding on the wheel that's been designed for the alloy that you're grinding. So they make aluminum grinding wheels and they make steel grinding wheels. Just make sure the grinding wheel has been designed for your actual type of material. Now, this video right here talks about grinding a little bit from SME. You want to watch that link on your own time. It goes through and it talks about dressing and truing a grinding wheel. We're going to talk about this individually in the slides instead of that video. So when we're surface grinding or when we're grinding, we have to take a real small depth of cut. The reason is the grinding wheel is running at a high surface speed. And if we took too big of a depth of cut, we would burn the workpiece and that's most likely going to destroy the heat treat that's been in our hardened workpiece. Or it's going to go ahead and just make the workpiece softer or put marks on the actual workpiece. So you use a real small depth of cut, usually less than about 5 thou, and you usually use some sort of cutting fluid to control that grinding temperature. So you're grinding with a cutting fluid and a small depth of cut. Now that wheel has to have a real good form to it because the wheel is actually imparting the surface finish on the part. So when you have a grinding wheel, you actually dress and true the grinding wheels after mounting it on the spindle. What that does is when you dress it, is you're basically grinding it so it improves the cutting action or cuts exact shape that you want it when you dress it. And when you true it, you're basically getting it nice and parallel or putting a shape into it that you want. So if you look down there in the bottom right corner, we have that part right there. That's going to be a thread grinding operation. So that's actually an industrial diamond wheel on the left side there that's shaping the grinding wheel that's on the right side. So the grinding wheel's in blue and the industrial diamond blade right there is putting a form into that wheel. So then it can go along and grind an actual gear right there. So dressing and truing gets your wheel to the correct shape and size for the grinding operation. Once it's been dressed and trued, we can go in and do one of our grinding operations. Now, this first operation right here is called surface grinding. In surface grinding, you grind nice flat surfaces. And you typically have a magnetic chuck, because most of the time parts that you're grinding are ferrous, they've been hardened, they're heat treated, and you're just getting a real nice surface finish on them or getting it down to a tight tolerance. Because when you heat treat something, it grows in size, and as it cools, when it shrinks back down, it ever so slightly distorts out of shape. So you got to do some finish grinding operations on heat treated parts to get them back into the right size or shape there. So this is going to be surface grinding. So this video here, this video here is showing an example of a set of shear blades getting surface ground. Let me turn the music or the sound off real quick. So what you're seeing are the set of shear blades. So if you've taken welding with Kevin, you've probably used the sheet metal shear to go ahead and cut your coupons. So these blades basically shear past each other and they are going to cut metal. So you need a real sharp edge and a real good surface finish and tight tolerance between these blades. So what they're doing is they're sharpening the top of them. They're resharpening the blades for the actual shear right there. And it's sitting on that magnetic table. The surface grinder goes back and forth. So it's moving over in the y-axis technically. If you're standing in front of it, it's moving towards us as we stand. So each pass it comes across and moves a little bit forward, and then it comes across again, making a nice flat surface. And again, that depth of cut is less than 5 thou. It's probably 2 or 3 thou that they're just taking off the top surface. So you can get a very accurate part with surface grinding. You can get into the 10,000ths of an inch or 4 decimal places with grinding operations. So that's a nice example of surface grinding right there. Now, so that's nice flat parts. If we have to do round parts like shafts, hardened shafts have to get grounds that have a real nice surface finish, or like pistons for actual shocks. If you think about like motorcycle shocks, bicycle shocks, they get cylindrical ground to a tight tolerance before they get plated. So what we're doing here in cylindrical grinding, it's a lot like a lathe where you have the workpiece is now going to rotate. And now you have a grinding wheel instead of a single point cutting tool. So that grinding wheel is going to remove a small amount of material and go down the diameter of that part. So this video right here shows an example of a surface grinder. It's going to be a very large surface grinder. If you remember back to IME 145, when I showed you the lathe video that showed the 36-foot long part on the lathe, this is the part getting ground afterwards. So what we have here is we have a 12 meter, not millimeter, roll grinder here. So this is a cylindrical grinder. It's basically rolling the part. You'll see that. And that's a long shaft, isn't it? So we've got that 36-foot long shaft. It's got to get a real tight tolerance and good surface finish. Because if you think about it, what the surface finish of the lathe leaves, it leaves a helix as it's coming down your part. In fact, I paused the video. You can see the surface right here ran a 76 thou chip load, if you remember that video. So that means every revolution, the tool moves 76 thou forward. So there's a 76 thou helix go spiral down that part. And if you're going to use that to maybe roll something out, like roll sheet metal out to a correct size, you want a smooth surface finish. So the traditional processes couldn't create that smooth surface finish. So what they're doing here is they're cylindrical grinding it afterwards. So the part on the left has been ground. The part on the right was the helix part that's going to get that surface finish removed. And the grinder basically just works its way down that part on that really old monochrome screen. Back when I was your age, that's what our screens looked like on our CNC machines. I didn't have color screens. So what we got here is cylindrical grinding. I think you get the idea, hopefully. Now, what we're going to do in lab, we're not able to hold on to the workpiece. So there's a process called centerless grinding out there. What centerless grinding does is it grinds the entire outside diameter in one shot. So we're going to do that in lab in week 6 to our pistons. We're going to make Delrin pistons for the air motor. And in order to get a really nice surface finish and a tight tolerance on that diameter, we're going to run them through a centerless grinder. Now, one side of the grinder has a grinding wheel. The other side of the grinder has a regulating wheel that has a slight cant to it. That slight cant causes what we call a thrust force. So when you put the workpiece in between them, that thrust force is going to carry the piston through the grinder in the case of the air motor project, or it carries the workpiece through the grinder. Now, we're also going to be pressing in dowel pins to the air motor. Those dowel pins have a plus or minus tolerance of 0.2 on some of them. Some of them are half a thou, depends on what you buy for a dowel pin. But they manufacture that dowel pin for 75 cents with a tight tolerance in the 4 decimal places, 0.2. So I can get a 0.2 tolerance with basically a pin using the centerless grinding. It's a fast process and I can get really tight tolerances. So this video right here is kind of showing you a rendition of it. It's a robotic cell right here that they're going to be doing some centerless grinding on carbide rods. So they're making really straight 330 millimeter carbide rods in this video. Now, on the centerless grinder. So the way it works, it's a machining cell. So they load the rods in here. This is the grinder in the back. So it's robotic, it's automated, Industry 4.0. So what happens is these are the rods that they got to grind straight. So it loads the rod into the machine. This will come right here. So loads the rod into the machine and it brings it into the centerless grinder right here. So notice it basically can grind the entire outside edge in one shot because you don't have to grind, you don't have to hold on to the outside diameter. Centerless, you don't have to hold it on by the center. So it grinds that entire rod and not much to see. It brings it out afterwards. And then we're going to check the run out tolerance on this rod. Remember that? We've done run out before, right? It's a dial indicator checking it. But look at the run out. No, barely any run out on the end of that 330 millimeter rod, thanks to centerless grinding. So that would be centerless grinding. So we have surface grinding, cylindrical grinding, centerless grinding, and the best of all, CNC grinding. So now in CNC grinding, these are how all of our taps are manufactured. So in order to cut a tap, you've got to cut hardened material. So they go ahead and they cut the flutes in the tap using a grinding wheel and the CNC grinder to get the actual helix up the tap. They also cut broaches this way. It's how they design broaches. It's how your solid carbide and high-speed steel end mills get the flutes ground into them. So it's how tools are made because they're hardened materials we have to machine. So in this video right here, we have a CNC grinder that's going to be making tool holders, right? Or no, this is grinding a hob. So this one, I'm sorry, the tool holders is coming next. So what this one's doing, it's a Haas, this is not the same Haas, it's a Haas grinder. Now they're grinding a gear hob. So this is a tool that makes gears later on, gear hobbing. So in order to cut that really hard tool, they have to use CNC grinding. So I'm going to come over here, actually is what I want to show you. I think it's right here. So in CNC grinding, you have a form tool. The CNC machine uses an industrial diamond to shape the grinding wheel in the exact form that you need. Hence the gear, the involute curve for the gear tooth right there is what they shaped it in. Then it basically goes along and it's not cutting in this video. It's just kind of showing you that it would be grinding it would be basically grinding that flute with that form cutter right there. They don't do any cutting in this video, unfortunately. We got one that does. So, whoops. This next video shows some CNC grinding when they're grinding on tooling cutters. So I'm gonna turn on the music for a second. And 1 second. Got the ad blocker going. So when we see this one, everyone likes this song, right? No? All right, we'll turn it off then. Oh yeah, I kind of like it. So this is our grinder. So these are Haas tool holders. The Cat 40 tool holders are made out of hardened steel. And in order to get that taper down to a precise tolerance, they actually grind the tool holder. Let me go full screen here. So this is how they make our tool holders. They cut them out the regular shape, then they go ahead and harden them, and then they grind them down to the final size right here. So what this thing's doing, let me move along. It's positioning itself on length. It's actually got a little probe right there that tells exactly where it is, right? So it just touched off to prove where it is. Then it's gonna dress the wheel. This is what I want to show you. That's an industrial diamond dressing the wheel. So it's squaring up the wheel and touching it off. So it knows exactly where the 0 point now is on the wheel. So now that the wheel's been dressed, it can grind the outside diameter automatically because it's CNC. Then it switches tools. It's CNC. Hold on. It switches tools to a little inside diameter grinder. So it's going to dress the inside diameter tool. So it's dressing that with the industrial diamond, making the right shape and touching it off. Then it brings that tool into the inside diameter there and does the inside of the actual tool holder. So that's CNC grinding. It's pretty much automated, and the grinding wheels get built with the CNC, get formed by the CNC machine to a specific shape. So that's the 4 major grinding processes: surface grinding, cylindrical grinding, center grinding, and then CNC grinding. 4 major processes in grinding. I know those 4. Now, there is a version of grinding that I don't really consider full on. It is machining, but I don't consider it a very accurate way to grind. It's called the belt sander. If you've ever been to a belt sander, if it's really coarse, you're going to do this week actually on the air motor project. You're going to use the abrasive belt sander to go ahead and put chamfers on our tool steel main shafts for our air motor. So these abrasive belts are used in the machining industry mainly for deburring only, or to remove a little stock off a casting. You don't normally use this for the final finish pass on the actual part right there. And so that's what it's all about for the abrasive belt grinding. It's just to kind of finish up work pieces or grind welds, clean up metal surfaces on castings. If you get a robot involved, though, it can get very accurate. But until you get the robot involved in the mix, abrasive belt grinding is not a very accurate machining process. But it's out there, so I put it on there. Now, if you remember when we talked about sawing, they make abrasive saws as well. They're called cutoff wheels. If you've ever used it like on a Dremel tool, that little abrasive disc that cuts things, all it is an abrasive mounted to a wheel or a disc. And cutoff wheels can cut steel, brass, aluminum. Just got to make sure you got the right cutoff wheel for the alloy you're cutting. So that traditional metal saw with the teeth continues to be a more economical method for cutting off large sections. However, when you have a real small section or something out in the field, you might be able to just cut it with an abrasive wheel very quickly. Now, if you have something hardened, like a sample for material science class, you have to use the abrasive cutoff saw to chop your sample up. Anything that's been hardened has to use an abrasive saw. You can't cut it with a traditional saw. So that's going to be all of our abrasive grinding and cutting processes. We're now going to get into detail on some of these are more finishing processes. So the first one we're going to talk about is honing. What honing does is it takes a rotating tool that has abrasives on the surface, and it basically finishes the bore, the internal bore of something. So it combines a rotating and a reciprocating motion to make a nice surface finish on the surface of your bore. So what honing does is it provides that final sizing. So if we had a GD&T call out of cylindricity inside of our part, we could go ahead and do some honing in there, and that's going to make it nice and round and straight and have axial and diametric straightness, both of those. So what you have is you have these expanding abrasive stones that they abrade against the surface, and remove small amounts of material. I'm talking like a thou. That's all you're taking off with the hone, about a thou or 2 thou. You're not taking off very much. So you have to have the hole there already, and basically to size. Honing is just improving the surface finish of the hole by removing a small amount of material. So what they've got here, they've got a honing machine. So this machine is honing gears. Gears rotate on shafts, and you want them to last a long time in that transmission, whatever type of transmission they're going into. So you want a really good surface finish on that hardened surface of that gear in order for it not to wear out over time as it rotates over and over and over. So what they're doing here is they're honing the inside diameter of that gear to get that good surface finish, and so it can sit there and ride on the actual shaft. So that's going to be what we got there is honing. Now they do it over here on this example. They're honing some rocker arms for an engine. So these are rocker arms for a dual overhead cam engine. And what they're doing is they're putting them on that fixture, and then the hone comes in and basically just line hones these two rocker arms together so they can rock back and forth on their actual assembly when they get put together. So that's what honing's all about. It's about improving the surface of your cylindrical bore. So it eliminates inaccuracies resulting from machining, and it gets you a really good cylindrical form. So a lot of most hydraulic cylinders are honed after we get the main part of the cylinder right there. Get you your final dimensional size for tight tolerance bores, honing. Now, engines are ball honed. So I know a lot of IMEs like engines, so we're going to talk a little bit about that real quick. Now, a ball hone has a bunch of abrasive balls at the end of it. And when you have a bore in a cylinder, boring, if you remember from IME 145, is enlarging a hole with a single point cutting tool. So what they do is they cast that engine block. They then use a boring tool to bore open the cylinder to the correct size. Once it's at the correct size, that single point cutting tool that was used to bore makes a spiral down the cylinder of that engine. So that spiral will actually cause spiral leakage. It won't seal the engine to make compression. So what they do is they bring in a honing tool or a ball hone to get that crosshatch pattern on the cylinder bore. So you see this cylinder right here on the left side hasn't been, on the left side of the engine block picture, hasn't been lined or basically honed, but it has on the right. You see the crosshatch pattern? That's a real smooth surface finish, that crosshatch pattern, that allows oil to kind of stick in the little dips and valleys right there, and it seals very well. So they ball hone engines. Now, honing was for holes or circles, right? Or bores. So if you didn't have a perfectly shaped bore and you wanted to go ahead and abrasive deburr the inside of a port, you could do abrasive flow machining. This one's really cool. This process is like you took Play-Doh to the beach and you dropped your Play-Doh in the sand and it got all a bunch of sand in it. Then you take your Play-Doh with a bunch of sand in it and force it through a port. When you force it through a port at high pressure, the abrasive grains remove small amounts of particle or small amounts of material from the workpiece in the direction of flow. So it actually makes those internal channels flow better because you're pushing through a putty with abrasives that actually are flowing in the direction of flow. So you have a hydraulic ram that forces that media into it, and it ends up basically taking precisely the shape of that passage or that workpiece as it flows through. So it's done heavily on aerospace and automotive castings to deburr them. This second video here, they're doing extrude hone on a bunch of Lamborghini and Ferrari heads to make power. Thought it was kind of cool. So watch that one. But what we're going to watch is we're going to watch Lance from Performance Diesel talk about how they do AFM in their exhaust manifolds to make it flow better. So after they cast their manifolds, they end up sending them out to extrude hone in Pennsylvania, which ends up doing this abrasive flow for them. So here it goes. So they got two manifolds bolted up together there. So they're doing two in one shot. So what they have is they have a profilometer there. That's what they're checking that thing with. Profilometer just checks the surface finish or surface roughness, so they can make sure that they got the required surface finish or roughness that that design requires. So that's what abrasive flow machining is. It's made for ports. Well, you probably didn't hear any of the sound because I didn't share my sound, but it's basically made for those ports that are irregularly shaped right there. So now next we've got lapping. So lapping is basically removal of material to produce some sort of nice, flat, high tolerance surface. Now the surface can be matte or it can be polished depending on the type of lap that you're actually using. So what lap is an abrasive slurry, or is a slurry. So you have abrasive particles mixed with water or oil-based liquid. That's what a slurry is. So slurry just has a bunch of abrasives floating around in some sort of liquid. Now a polish is a slurry. So car polish or car wax, like cleaner wax, has a small abrasives in it to remove that clear coat that's kind of fogged up. So you remove a layer of clear coat to get your car nice and shiny. So polishing is almost like hand lapping. That's what polishing is. But true lapping uses a lapping table or a lapping plate. Let's talk about this a little bit more. So the lapping machine will produce extreme dimensional accuracy here. So we can get down to basically the very smooth surface finish. If you look, lapping gets the smoothest surface finish and the tightest tolerance out of any of the processes. What's really happening here is we have an abrasive that's charged on a felt wheel. So there's like a wheel that's a lot like a record player. It rotates, and you put the abrasive slurry down on that felt disc. You then put the part down on it and you put pressure down on it. That pressure, it allows the abrasive slurry to remove small amounts of material off that surface when it touches the surface. So there's automatic lapping and there's hand lapping. So this first video right here is going to show you some automatic lapping basically on a finishing machine here. It's going to do this. So give me 1 second. We'll go full screen. You can now hear it at least. You don't even. So looking at it, we've got the slurry being thrown on the table. The parts are underneath it. These are just weights on top of the part. The parts are actually underneath that. And all they're doing is removing a small amount, finishing the surface of that part to a real smooth surface finish. It does this for like a minute and a half. It continues to go. And they get a nice orbital motion. So you're not basically putting swirl marks in your part. That's lapping. This next one, they're lapping lenses. So if you think about it, once you cut a lens for a camera or something like that, you've got to go ahead and polish it so it's nice and smooth. This one's got some. You missed the Miley Cyrus because the sound wasn't hooked up. But anyways, so we're lapping a lens right here. So they go around, there's a slurry being poured on it. And we're slowly polishing that lens. Here's some more. It's lapping, really. They call it plano polishing. It's lapping. It's a true process. Cool. And that's the slurry right there. So it's dirty looking because those are the abrasives inside that liquid. So lapping by a machine. Now, hand lapping can be done on a lapping plate. So if you've ever seen a cast iron plate like this that has grooves in it, what you do is you add lapping compound, which is a slurry. So it's like an oily mixture of abrasive and like a grease. And you basically do figure-8 movements on that cast iron plate. What that does is it breaks down all of the peaks that are on that surface finish and removes them. So you have a really smooth surface finish on your part. So you do hand lapping like on steel parts or ferrous parts. Now, the surface plates that we've been using as a datum surface, they got nice and flat because they were lapped. So what this gentleman has up here is a laser interferometer. He's able to tell the high sides and the low sides of this surface plate. When you have the high sides, you need to get the lapping plate out and lap it down so it's nice and flat. So to recondition a surface plate or to qualify it, you measure across it, you figure out where it's not flat, and you basically lap the top or the high sides out so the whole thing's nice and flat. Like our surface plate was flat within 9 millionths across the entire plate back when it was first calibrated. That's 9 millionths across the whole pack. That's 6 decimal places. So that's going to be what hand lap is. That's how they hand lap surface plates back to the right size. So in this class, we're now done talking about most of the machining. We're done about talking about the machining processes. We've been through conventional machining, non-traditional machining process, abrasive machining processes. And hopefully you've seen, as we went from conventional up here where we got sawing, drilling, milling, broaching, we didn't get as nice of a surface finish as we would have if we were lapping or we were polishing. So I really like to show you this chart because it kind of shows machining processes versus surface finish. And surface finish and tolerance go hand in hand. So the better surface finish you can get, the tighter a tolerance you can get out of your part right there. So if you look with lapping, we can get down to basically 0.025 or basically 1 micro inch, at 0.025 of a micrometer. It's pretty impressive for surface finish. Where in machining, most of the stuff that you machined in class, I would say those Geneva drive wheels are probably about a 60, probably like a 40 surface finish, between 63 and 32 for our milling. So I know it says you can barely get past the 63, but you can get down to a 32. I'd say we're better than 63 on those Geneva drive wheels. We're pretty close to probably in the 50s, maybe high 40s. But we could test it with a profilometer. But that kind of shows you how all these machining processes work in terms of surface finish and tolerance. So we're going to start the air motor manufacturing project next week. Technically, it's week 6 in lab. So during week 6 in lab, you're going to start working on 4 parts in lab, and you're going to get into groups. This has been designed to kind of be an anti-stress project to the end of the year. I know you're all IMEs, you're starting to ramp up in your other classes. We're going to produce air motors this year and then call it good. We're going to have basically we're going to have a couple more assignments, and pretty much that's it. We're going to produce air motors in groups in lab. So come to lab, read through the air motor project introduction in your lab manual before you show up to lab. And then we're gonna go from there. We're gonna be doing some abrasive machining in lab in week 6, where we use the belt sander to chamfer our main shafts, and we use the centerless grinder to go ahead and centerless grind our pistons. So I'll talk to you next week. Next week's pre-lab is going to be a real short one. It's just going to kind of be a review of what's going on with the air motor project for you. And the week after that, I'll go ahead and review the cost report for the air motor. Then the week after that, I'll go ahead and do a final exam review for you. Then we're in week 10 at that point, where we go ahead, take our final, and finish up our air motors and call it a year. We'll go off to summer. So thank you for joining this week for our pre-lab. Enjoy week number 6 in IME 146, and I'll see you around campus. Have a great day, everybody.